The second lecture by Marco Kormos.
Yeah, okay. So, to save some time, I want to hand out these. So these are handwritten, sorry for not preparing a proper PDF. So just to speed up things a little bit, this is only a collection of formulas for the change of variables when we change from rapidity to quasi-momenta. Okay. So before that, like talking to some of you after my previous lecture, some things came up, maybe they need to be clarified a little bit. So just to recapitulate, the Hamiltonian I won't write down again, but so as we remember, we managed to map this Hamiltonian to quite easily to a system of hopping particles. The particle goes on a lattice. Okay, this is a very simple picture, and I choose my reference state as this state. Okay, this is the reference state. Just because I want to associate a hole with a downspin and a particle with an outspin. It's as simple as that, okay? And this doesn't mean that this state is the ground state. Actually, it is, of course, in the ferromagnetic regime, but it is not in the other regimes. But if you think about, if you think in terms of particles, how you write down an many-body wave function, you have a reference state, a vacuum, right? And then you act with creation operators on it. Okay? I don't know, something like this. Or even in real space, you can imagine that we have some creation operators. And this is the same what we do here. So this is just a reference state of vacuum, and we write that, we write the eigenstates of the Hamiltonian energy eigenstates as linear combinations of states, and in each term in this big linear combination is something like this when we act with creation operators on this state. Okay, so. And in these terms, you can understand the beta-ansatz wave function. If you think about in terms of particles, so upspin particle, downspin and all, it's very similar to Jean-Sébastien Paul's beta-ansatz wave function. Okay. Good. Yeah, and as I advertised, there are many conventions in the literature. So as you might have noticed in Fabian Ester's lecture, he defined the Hamiltonian with an overall minus sign with respect to mine. Luckily, the magnetic field included, so it's really an overall minus sign. So this is why the space diagram was reversed right there. Okay. But other than that, we are talking about the same thing. Okay. So you have before you now this crazy collection of formulas. So as I said last time, we want to make this change of coordinates, a change of variables, in order to simplify formulas. It's not obvious that this brings some simplification, but we'll see that it does. So let me go through maybe the first column of this, and then I don't have to do it for each one, right? It's the same with the slide change. So let's start with this regime. So delta smaller than minus 2. Okay, maybe just before that, it's worth reminding ourselves of the space diagram, just to be sure that we're talking about the same thing. So this is the magnetization. Then, if you remember, this was a ferromagnetic regime. And here we have an antiferromagnetic order, zero magnetization, and this was a gapless phase here between -1 and 1. Okay. So is it clear what gap and gapless means? Because I didn't really explain that yet.
So you showed when you read the reference that it was indeed gapless. I mean some phases, but in the very beginning of yesterday or the day before later, you had an argument about how you could see from the elementary excitations that, for instance, the ferromagnetic phase was gap. And could you maybe repeat that? Because it didn't seem clear to me that really the smallest excitations were corresponding to something gap. They were finite anyway, so I don't get there.
They were finite?
I mean, the small excitations were anyway just flipping a spin, so the change of energy was something like that. And I don't see how necessarily it ends up in something else. Could you maybe explain that a bit?
Yeah, okay, so this yeah, so eventually the excitations will be equivalent to spin flips. So if you think about one spin flip as one particle and you study just the dispersion relation of that one particle, yeah, as we saw, it already gives us some idea about whether it's gapless or gap. But today I will be more careful, and so I will derive the spectrum of excitations, and you will see that this derivation is correct in the sense that the identification of phases was correct. So we will see that here we will have elementary excitations above the ground state. Actually, maybe this is your. Now I understand. So maybe what is? Let me ask you whether this is your question. So when we draw the single particle dispersion, of course this is above this reference state, right? And maybe you're saying that we should look at the ground state and study elementary excitations above the ground state.
No, the thing is that even before looking at this dispersion relation, just saying that okay, we know that in the ferromagnetic phase, the ground state is all spinning in the same direction, and excitations will be like that, and they will cause this. You were able, I mean, you seemed able to say just from that, okay, so this is a gap phase, and this I don't get. I mean, before having the dispersion spectrum is something like that, so this is
So I mean, if you flip once, yeah. So I think in that phase, this is really an excitation of above the ground state, and it has a minimum energy, right? So this is what I mean by gap. And the gap was proportional with delta, right?
Yeah, but even in critical phase, the excitations have a minimum energy, right? When you consider a finite system. I mean, what matters is what happens when you go to the thermodynamic.
Okay, so this is, exactly. So this is why I'm saying that you will see that first we will construct the ground state in each phase, and then we will study excitations above the ground state in the thermodynamic limit. And probably that will answer and this is the proper thing to do, I think. So, okay, yeah. And we also drew this in a slightly different way. If we think in terms of the chemical potential or the magnetic field, then we found that there's an upper critical magnetic field above which all spins are aligned, right? Because it's strong enough simply to align the spins. So this was this ferromagnetic, and everything is symmetric, of course, with respect to as it goes to minus z. And here there was this curve starting somehow like this. And this is some lower critical magnetic field. So what this means is that here an infinitesimal magnetic field will give you some finite magnetization. Okay? But here, okay, sorry, so this is antiferromagnetic, okay, and this is I call gap, this is gap and this is gapless. And this means that here you need a minimum magnetic field to break this order. So this antiferromagnetic order is associated with zero magnetization, right? So in order to achieve a finite magnetization, you need a finite magnetic field, and this again we will calculate today. Okay, so now let's go back to this this formula. So in this regime, so here we choose let me write just the second formula here. So we change from the pseudo-momenta or quasi-momenta k to some variables which we call lambda, or we denote by lambda, and we call them rapidities. Okay, so we can think about this as for the Bose gas, 1D Bose gas, these quasi-momenta and the rapidities coincide. So we didn't need this step, right? If you remember. But well, it just happens that in this system we need this intermediate step. So K is 2 arctan. Okay, so what does this mean? Well, this follows from this one. Okay, so this if you don't believe, it's an exercise to do it. And then we will need, you will see why, we will need the derivative of this quasi-moment with respect to the new variable, the rapidity. And then this, of course, is quite easy to work out. You get something like this. And there's a useful relation. It's not completely clear why I'm interested in cosine k, but no, actually it's quite clear, because if you remember, the one particle dispersion relation had delta minus cosine k. So if we have a simple expression like this, that's useful. So k prime lambda is just this, right? Okay, and what else? And then, okay, so this was for the momentum. But the point in all this is that using the new variables, the phase shift will be translational invariant. So I think this is the main thing. And actually, okay, of course, really must country. So you see, it only depends on the rapidity difference, and you also see that yeah, maybe let's make one more step. So again, you can solve this for theta, and what you have is right. Arctan so I hope it's readable, my handwriting on that sheet. Something like this. Okay, you can. Well, it's not that important for us now. This just makes this term makes this function continuous. So what I wanted to point out is that if you look at the expression for k and theta, you see that it's almost the same function. The only difference is that we have eta half here and we have eta here. So this will be very useful when we manipulate these expressions. The fact that these two functions are very similar is very useful. Okay, so then we have everything to write down the beta equations again. So if you remember, beta equation was something like this, right? Like and here there was a big product. Okay, so now we can rewrite this in terms of probabilities, and you can see maybe you can see what we get this equation here. So it's a product of trigonometric functions or hyperbolic functions in the other regimes. Okay, so let me skip that step, and as I said, the energy, which was just this, okay, minus 2h if you have some magnetic field. Because of this relation here, we can write as sum over lambda.
Excuse me.
Yes.
How can it depend just on lambda and not on the difference lambda minus lambda prime? With the equation for theta. How comes it depends on just lambda, not the difference? I mean, the exponential depends on the difference.
You mean here?
Yeah, exactly.
Ah, okay, so that's a mistake. So, okay, lambda minus lambda prime. Sorry. Thank you. So, so we had these beta equations, and just like in the case with the Bose-Gas, this is a coupled set of nonlinear equations, and we have to solve for the set of the rapidities. Because if you remember, the beta wave function has and the parameters of the beta wave function are the quasi-momenta. Okay, so once we solve this came from the periodic boundary conditions, then we have an eigenstate with the correct boundary conditions. Okay, so if you have a set of k, of course, then we have a set of lambda if you wish. So these are the lambdas I'm summing over here. Okay. All right. So and then we take the log of these beta equations, and then we find something like this. Okay. And here I use a notation. I use this notation that this is basically, I can call it lambda and eta half, just because here we have eta half, and then with this convention, this is just lambda minus lambda prime. Okay, so this is very dry and not very exciting. We have to go with this. Okay, so let's see now what we can get using this new expression. So before that, let's say a few words about long range order. So, okay, the easiest thing is delta greater than 1. We have ferromagnetic order. So the ground state is doubly degenerate, right? So either all spins up or all spins down. So we can write down the correlation function, which is just this, right, independently of I and j. Okay, so what happens in the opposite case when delta is smaller than -1? So again, let's start with delta goes to -infinity, which is just the antiferromagnetic easing model. When delta is really -infinity, then we have a double degenerate ground state again, the snail state, and we can call this anti-nail. Okay, so these have energies. I think we already discussed this. So again, if you are interested in some correlation function of the spins, then it's quite clear that the result is -1 y minus j over 4. So there's a staggered magnetic order. And so you can ask what happens as delta when we decrease the absolute value of delta. So it's still smaller than -1, but finite. So then it turns out it's very hard to say anything about this correlation function. So we know that there's no order. So there's a finite value of this correlation for large I and j. Okay. So we expect that in this case we can write this for large I and j in this form. So this is some constant. This P0 is something that is a constant. This is just because it's a staggered thing. And Baxter derived a very nice result. It turns out that n times eta. So I realized probably I forgot to mention that so eta appears everywhere in my formulas, right? So you didn't ask what eta is related to the anisotropy delta in this way. Okay. In the other regime, we use a different parameter, which you can think of this as an imaginary eta. I denoted it by gamma, so minus cosine gamma is delta. Okay, and also for this there are many conventions. So how to document the probabilities? Okay, so in every book you find a different parameterization. But I think this is the one I gave you was I checked that the formulas are correct. Okay, so sorry. So if this is the definition of eta, then it turns out that this correlation function is given by this expression. So let's draw it in as a function of delta. And it goes okay. So of course here it's 1/4 this value, and it's clear that it vanishes when we reach the delta equals -1 point. Okay, so this is the order phase. There is no order here, so it's long range. This correlation function vanishes. Okay.
Sorry, what are you talking about?
Sorry.
What is the function there? P0.
I'm quoting yes, P0. this value is no, sorry. No, I'm plotting, let's say, okay. If I'm plotting P0, then of course this is 1. The shape of the curve is very similar. So I can cheat a little bit. Yeah, so P0 approaches 1 for large anisotropy, negative anisotropy, and it vanishes when we go to delta. You can check. Go to delta minus 1. So this is the phase. This is a phase transition, right? From antiferromagnetic order to non-order state.
So sorry, where does that result come from?
Well, that's, I don't know. I know, but it's not derived from the Bethe wave function. I think it was derived by exploiting the relation between the XXZ model and the 6-vertex model, which is a statistical physical integrable lattice model. Okay. So I just wanted to mention this as a well-known famous result, but we cannot derive it with our tools at this moment. Okay, so I guess I can read this. So this is what I wanted to say about this, these ordered phases. And now comes something more interesting, I think. So okay, so I just erased it. So the Bethe equations look like let's see. Yeah. What was exactly the form I used? Let's okay. This was this function eta half eta. Okay, so lambda prime and okay, so if you remember in Jean Sebastian's lectures, now we are interested in the thermodynamic limit, so we will do the same trick. The point is that these equations are very hard to solve, as I said. Of course, numerically one can try to find the solutions, but things simplify if you go to the thermodynamic limit, and we are interested in that anyway. So let me introduce, following the case of the Bose gas, let me introduce a function so this I alpha, these are integers and half integers. I can define a function, a continuous function, as a function of these rapidities. Sorry, this is lambda. Why I have alpha? So this function takes the correct values of integers and half integers as we sweep through the rapidity variables. So the point is that in the thermodynamic limit, the rapidities become very dense, right? So we want to think in terms of smooth functions, and this function f satisfies this relation. So the derivative with respect to lambda is the derivative gives you the density of the energy level. Okay, so this is exactly the same as for the Bose gas. And okay, I guess, okay, let me correct this a little bit. So I want to call this I over n f. Okay, so then we can think in terms of continuous functions. So this sum becomes an integral over rapidities. Yeah. So this is a function of lambda. Okay. So this is a very standard thing to do. We have this set of m equations, and in thermodynamic limit we turn it into an integral equation. Okay. So now here I made an assumption, which is that I'm talking about the field Kormos. So here, when I turn this sum into an integral, I need the density of the field states, right? The density of particles or solutions of these equations. And if you remember from the lecture about from Grand-Sebastian lecture, one can define the density of roots and density of holes. So some of these energy levels are filled, some of them are not filled. But I'm talking about the ground state, and the ground state is given by a field Kormos. So the density of energy levels coincides with the density of the roots or the density of field levels. So this is why I can use the same rule here and here. Okay. When we talk about thermodynamics, then of course there will be excitations, particle excitations, so there I should use a different function here, as we'll see. Okay? So why do I say that the ground state is a field Kormos of probabilities? Well, one idea is that if we go to delta, the delta equals 0 point, which is equivalent to 3 fermions, as we saw in Fabian and Essel's lectures, then we know that the ground state for 3 fermions is a field Kormos. Okay? And then just by continuity, if I change delta, these integers are not supposed to change. So we expect that also for finite delta we will have a Fermi, perfectly filled Kormos.
But eta isn't defined for delta equals 0.
Sorry?
Eta is only defined for delta less than -1.
Ah, okay. Okay, so what sure. But what I'm doing here is you can repeat it for the other two phases. Okay. This is we are starting with in this phase, but the derivation is exactly analogous. As you see, the only changes are you change signs to hyperbolic sign and stuff like that. You're right. Okay, so when I talk about this phase, maybe I should talk about I should use this other notation in gamma, but that's not very crucial. Okay, so the ground state is a field Kormos. So again, just going back to what I said at the beginning, we have the reference state all spins down, and this is a highly excited state if delta is smaller than 1, or even smaller than -1. So there will be a macroscopic number of excitations, right, in this vacuum, and this is what we want to describe in the thermodynamic limit. Okay, so in this sense you can think about field Kormos. And the interesting thing is that unlike the case of the linear model, here we can solve explicitly these integral equations in a special case, which is, however, an interesting case, which is the hard field lattice. What I mean by hard field is, of course, that the total magnetization is 0. And as we will see, this corresponds to the external magnetic field being 0. Okay? So if you look at these formulas on that sheet, you will see that for delta smaller than -1, the maximum values lambda can take is so lambda runs between -pi and pi. So this is the maximum value it can take, and in this regime, actually it can run from -∞ to infinity. Okay? And I'm only looking at these regimes because the ground state is trivial in the delta greater than 1 case. Okay? So I want to look at the situation when so I didn't tell you the range of this integration, the boundaries of the integration, right? So let's denote it by a Q. Okay, so it's a symmetric firmacy, so this is divided with -Q and Q. And let me consider the case when Q is actually Q takes its maximal value. So either pi in the first case or infinity in the second case. Okay. So it's not a priori clear why this corresponds to the half field lattice, but we will see that this is the case. Okay. So why do we like this? Because now the equations become completely translationally invariant. Okay. And these equations are linear, so we can use Fourier transform to solve them. So how it works? Let me start using a simplified notation. Okay, one more step I forgot is that we differentiate this equation, and using this property let me call this K lambda minus lambda prime. So this is the kernel of the integral equation. So now you see that so this is an integral equation for the function rho. Okay, the linear integral equation, because rho appears here, and this is a known function, right? And this is the equation we want to solve. So let me write this equation in this form. Okay? So what this means is that I'm acting with integral operators, if you wish. Identity plus this K integral operator on rho. By this I mean that I have to take the convolution of these. So this corresponds to the Dirac delta function. And this corresponds to this kernel function, and this product here means that I have to take the convolution. Okay, so then you see that this is nothing else but this equation in a more compact form. Is it clear? Is it just to simplify our life? Because now. Let me define another operator with this implicit way. Okay, so I is this identity, and I define this operator R, which I call resolvent operator. So this is somehow, my goal is to invert this, right? I'm interested in rho, so I want to invert this operator. Is it clear? So now to this end I define this R operator. This is again a very common thing to do in these K-tensor solvable models. If we write this out, then you see that it's that actually 1 minus K times R is K. Okay? So the resolvent operator satisfies another integral equation of the same form, with the same kernel, but with a different source term. Okay? So, do you want me to write out that equation, or is it clear that it has this form? Here I have some rho lambda function. Sorry, R lambda, here again an R lambda function, and here as a source I have the kernel itself. Okay? And as you will see, the integral equation with the same structure will pop up all the time. The same kernel, and the only difference will be in the source term. Okay? So why is this good? Because let's take a Fourier transform. Okay? So this multiplication is implicit in this notation. Again, meant a convolution. Okay, and as we know, if we go Fourier space, this becomes really ordinary multiplication. So let me take the Fourier transform of these guys, and then I denote Fourier transforms by tilde. Then now it's easy to invert this, right? So R is nothing else but K tilde 1 plus K tilde. So this is R. And even more interestingly, rho tilde is nothing else but 1 over 2 pi K prime tilde. So this is a small k over 1 plus K tilde. Okay? Right. So let's see what. So this is very straightforward, I think. So let's see how this works in practice. So let me go through these 3 regimes, actually 2 regimes and the isotropic point. So first case delta is smaller than -1. So we will need from that sheet I gave you K prime lambda. So let me write it again. So again, eta is related to delta, and lambda is the rapidity. That's my new variable. It's equivalent to the quasi-momentum in some sense. What else? I need theta prime, which is of course the same thing with 2 eta. It's a function of lambda. Okay? So first step, we need the Fourier transform of K. Okay? So we need the Fourier transform of this function. Actually, it's a Fourier series now, because in this regime, this antiferromagnetic regime, lambda runs from -pi to pi. Okay? And there's a periodicity. So I need to take the Fourier series of this function. So kernel. So the kernel was 1 over 2 pi this. Okay? surprisingly simple. Just this. Okay? So now we can easily find R tilde, which is again K tilde over 1 plus K tilde. So this, and finally rho tilde. So it's going by this formula. So the result is this is n. Okay, so 1 over hyperbolic cosine. This is our solution in Fourier space. Okay, so it's surprisingly simple. And so what we need to do is take the inverse. So we have to sum up the Fourier series, and well, it can be done in closed form. It's not very nice, but okay, let's see. It's this series, and well, you can write it in terms of elliptic functions. It's not, if you're not familiar with elliptic functions, it's not necessarily illuminating, but so there's this elliptic integral k. Well, just to be, for the sake of completeness, I give you the definition of k. Is this integral?
The equation for rho tilde n, the middle doesn't equal the right hand side, I don't think. There's some minus sign in either the top or bottom exponent.
So this must be plus, right? Is this your...
Yeah, or the bottom one's minus.
Yeah, probably just type in minus, yeah, because... right. Yes, because so the Fourier transform of this is this. Yeah. Okay. So clearly the Fourier transform of k, little k prime will be with the half theta, and then this is what. Yeah. Okay. And what is m? I missed. So m is defined again implicitly. Okay, this is just to show that if you want, you can write the result in an explicit closed form. But the point is that so in Fourier space it's extremely simple, and then you can take the Fourier transform to obtain the rho lambda function. So I use a rho 0 here. This is half-filled case, zero magnetization case. Okay, so that's good. But now you can ask me, well, what does this correspond to? What I did was setting the range of integration to the maximum possible value. So, well, let's calculate the magnetization. So let's calculate the filling, which is nothing else but this, right? From minus pi to pi. So the tricky way to do it, you can try to do it here, but of course it's much easier to just take the Fourier transform, the zeros Fourier mode. n equals 0 here. We have one half. Okay, so now we see that this is the SZ total SZ0 case. Okay. And okay, maybe as last step we can compute the energy, the ground state energy. So we use again a formula from our collection. There's a formula on that sheet with a discrete sum. Now we turn it into an integral. Right. So we have to sum this. This was, if you remember, this was delta minus cosine k. With this, in this parameterization, it looked like this. And I have to integrate this with the density. And, okay. What you find, it's easiest again is to go back to Fourier space. And this is the result. So it's an infinite series, but one thing that we can check just for consistency is that if eta goes to infinity, what is eta goes to infinity in this case? Delta goes to minus infinity, right? We should get back our naive picture about the easing antiferromagnet. So, of course, if eta goes to infinity, then all terms seem to vanish here, except, so here n goes to minus infinity to infinity, so there is a n equals 0 term, right? And this is 1. All the other terms vanish. So we find minus j times sinh eta. As for large eta, sinh eta and cosh eta are the same. So this is nothing else but delta. And this is exactly what we expected for the ground state energy of the easing antiferromagnet. Okay, so this is probably a bit dry, but so this is how it works basically. We are massaging these integral equations a lot, and in some cases we can find explicit results. So yeah, probably we shouldn't underappreciate the fact that we have formulas for the exact ground state energy of this interacting model, or interacting many-body system if you wish, right? In the thermodynamic limit, this is the energy, the ground state energy, for all possible values of delta so far in this regime. Okay. So probably there are a lot of steps that were somewhat new to you. So if maybe I stop for a second for questions. And before the break, I just want to just list the results quickly for the other regimes, and then maybe that's a good point to take a break. So, do you have any questions? So maybe I just summarize what we did here. So we had the beta equations, okay, which are again a set of nonlinear equations. In the thermodynamic limit, we can introduce continuous density functions, basically density of states, density of field states, density of holes. This I haven't used yet, but the point is that this set of equations turns into an integral equation. This is the same as for the bosons, and then this integral equation is for the rho. In this case, is a linear integral equation. So to solve it on a computer is quite easy, actually. And it can be solved to basically arbitrary precision. And more than that, in this special case, half-field case, we exploiting the translational invariance of the equation and the kernel. So you see that it's important that the kernel in the new variables is translationally invariant. We can take Fourier transforms and we can solve this linear integral equation. So this is all what we did. And this way we have the exact probability distribution and exact ground state energy. Okay? And we confirm that what we did was the half-field case by computing the integral of the density. So what we can do clearly, we can repeat the same derivation for delta between -1 and 1, so the paramagnet. And I think you can imagine how it goes now. So we have to change a few formulas, but let me just give you the result for rho. So this is the equivalent of this, yeah, right? But now we have integration boundaries -infinity and infinity. So these are really Fourier transforms, not a Fourier series. So this will be a function of some omega, okay? And probably it's not very surprising, we have the same functional form. And in this case, we can take the inverse Fourier transform to obtain the density of lambda, and explicitly it's somewhat simpler. Instead of elliptic functions, now it's 1 over cos. And again, if you want, you can integrate it to calculate the filling. And the easiest is just take this function at omega 0, so it will be 1/2. And the energy per side, so E over N, ground state energy per side. Well, even in terms of a Fourier transform or integral in the frequency space. So just for the sake of completeness, copy it here. Okay, so it cannot be written in a nicer form. Yeah, what can we do? Here is, well, you can check the delta 0 case. When gamma is pi half, you get back what you expect for a free Fermi. Okay, so this is a nice and very simple exercise. And finally, for the XXX antiferromagnet, so delta is -1 in my language, if you remember. Maybe we could start with this because this is the easiest and simplest. So the kernel, okay, I didn't write the kernel here, but the function of omega is just e to minus omega absolute value, and then rho of omega, rho 0 of omega is given by this. Again, you can integrate this to find that we have half filling, and the ground state energy is given by, yeah, maybe this is worth mentioning. Is minus J times mod 2. This is the ground state energy of the Heisenberg antiferromagnet. And if you remember that the Hamiltonian in this case had this form. We can immediately calculate the expectation value of this product, right? And because there is this is an isotropic case, this is nothing else but products in x, y, and z directions. So now you use that E over N is this, you plug it in here, you divide by 3, reordering terms, and what you find is this. Okay. One thing that we have to be careful about is that when we use this convention, we flip every other spin, to remember. Instead of talking about delta equals 1 and negative j, we have positive j, but delta equals minus 1. So we have to multiply by minus 1. So this is the exact next nearest neighbor correlation function for the in the ground state of the zero magnetization XXX antiferromagnet. Okay, but to compute, let's say, did I say next nearest? I meant nearest neighbor, of course. So the next nearest neighbor, jj plus 2, is already hard to compute, obviously. Okay. So maybe this is a good time to have a break. And yeah, I guess 10 minutes.
Thank you.